All right. So now we'll talk about conservation of energy with friction. Okay. So we have learned so far that total mechanical energy is the sum of kinetic energy plus the potential energy. Okay. We care about the change, so work done equals to change in kinetic energy, which is equals to negative change in potential energy. So if you rewrite this, work done equals to change in kinetic energy plus change in potential energy, which is equals to 0. Or we can also write that as kinetic energy final plus potential energy final equals to kinetic energy initial plus potential energy initial. Okay, this is what we have learned so far. Change in mechanical energy equals to change in kinetic energy plus change in potential energy equals to 0. So what type of energy exists at each state? 1, 2, and 3. So at 1, okay, everything is in the form of potential. At 2, this will be sliding, so everything will be in terms of kinetic. So now going from 2 to 3, it gets stopped due to friction. Okay, while being stopped by friction, there is friction creates this heat, okay, which is a thermal energy. Okay, there's no such thing as frictional energy. Friction is the force. Okay, when that force has been applied, okay, when it does that work on an object, okay, it generates that energy is transferred in the form of thermal energy. Okay, let's see how we calculate that. Okay, so what does thermal energy mean? Energy associated with the random motion of atoms and molecules in a system. So when you have a solid, okay, molecules are closely bound. So if you look at liquid, like molecules are not closely bound. Okay, in a gas, molecules are far apart. Okay, intermolecular systems. So you can convert, like let's say for example, you have a bowl of ice. Okay, you put that on top of the stove. Okay, molecule starts to get far apart, which converts into liquid, and then uh, when you when you heat that water, it converts into steam. Okay, you can do this experiment yourself. So let's say you're boiling a water. Okay, so you're boiling a water boils at about 100 degrees centigrades. Okay, so if you just put your finger, or don't try this too much, but like you must have noticed this, like the steam around, okay, is much hotter than the water itself because of the movement of the particle, right? So when we had no friction, okay, so work done equals to change in mechanical energy, which was sum of kinetic energy plus sum of potential energy. Now we are adding this E thermal. Okay, so work done equals to, when there is friction, we add this thermal energy. Okay, change in mechanical energy, change in mechanical energy equals to change in thermal energy. So we had this term, we are adding this extra term now. Okay, so in this case, so when there is friction, okay, when there is friction, this kinetic energy 2 plus potential energy 2 equals to kinetic energy plus 1 potential energy, but that does not work. That is not true anymore. Okay. So with friction, how does that, so we measure that thermal energy. Okay, so in the previous exam problem where I saw that slide, like that, thermal energy is calculated by work done by object by friction. Okay, so work done by friction, okay, force friction times the displacement. Okay. So here we can write this. Okay, so this part was pretty much mech 2, right, equals to E mechanical 1, right? So that was equals to 0. Okay, that was what it was. Okay, so let's say I started with some amount. okay, some amount of work done, okay. So I had, like, say, initial energy at point 2, okay, or at point 1, okay. So I had some energy at point 1, okay. Now because of friction, I would not have the same amount of energy at point 2, okay, the total mechanical energy. So whatever I have is lost, okay. So to specify that, so this would be E initial E mechanical 2 was E mech 1. So the one way to write that is whatever the initial energy I had is lost, so I don't have the same amount, so that is E thermal, okay. Or, so now other way to write this is E mechanical 2. So now I don't have the same energy, like, so I can add that on this side too, however you want to look at it, okay. So to calculate that, we use, okay, so to calculate thermal, we use friction, force friction, okay. Energy an external force can do work on the system, okay. So when you do work on the system, okay, you're doing a positive work. When system does work on you, okay, negative work is done, okay. If a system is isolated, the total E cannot change, okay, if in a total isolated system, okay. So in that case, we have to consider the internal energy as well, okay. For now, we are going to consider that internal energy to be 0. All right, let's solve a problem. A 70-kilogram person slides down a frictionless water slide. The height of the slide is 20 meters. What is the velocity when they reach the end of the slide? All right, so E mech, so I would start with this, that is change in K plus change in U equals to 0. So I can write K1 plus U1 equals to K2 plus U2. Okay, initially kinetic energy initially is 0. Okay, at this point potential energy is 0. So if I consider this to be a 0 point, so mgh 1/2 mv squared, mass cancels out, v squared is 2 square root of 2gh. Plugging in the value height to be 20 meters, I get that to be approximately 19.8 meters per second. Okay, so now let's say at the bottom of the slide, this person lands in a mud pit and the coefficient of kinetic friction between them is 0.4. The person lands in the mud and slides to stop. From the starting at the top of the slide to when they come to a stop, how much work is done by gravity, normal force, friction? Okay, how far from the bottom of the slide does the person stop? Is the E mech conserved? Where did that energy go? All right, so let's calculate all that. A, work done by gravity. So gravity just does the work between this height here. So that would be force gravity, d cosine of 0 degrees. Mass is 70, g is 9.8, okay? And then height is 20, so that is 1.37 times 10 to the power 4 joule. B, okay? Work done by force normal. So force normal is force normal, d cosine of 90 degrees, okay? So cosine of 90, so that is 0 joules. Work done by friction, mu mg d cosine of 180, okay? While the person is here, friction is in the opposite direction, okay? How far from the bottom of the D is how far So that is work done by friction. So while friction does the work, okay, work net equals to change in kinetic energy, which is kinetic energy final minus kinetic energy initial. Okay, kinetic energy final is 0, so that is negative 1/2 mv initial squared. Okay, so whatever the energy the person initially had, okay, by the time that person reaches to this point, everything is lost. Okay, energy initial equals to energy final, so that is, I can say that because they come to rest and this it's not moving. Okay, friction, because of friction you lose all that energy. Okay, so the other way to write that down, so work net equals to change in kinetic energy, which is negative work done by friction. Friction did the negative work. Okay, 1/2 mv initial squared. Okay, 1/2 mv final squared. So final was at rest, so negative work done by friction. So 1/2 mv initial squared minus mu k mgd friction. Okay, this is friction kinetic. Negative cancels out, mass cancels out. From here we can find the displacement. Okay, or oh sorry, my bad, let me redo this part. I deviated away from. So we know we had that initial energy, right? Initial energy was in the form of gravitational potential, which was 3720 joules. Work done by friction, mu k mgd. So we are supposed to find d. G. So calculating all that, you get 50 meters. So mechanical energy is definitely not conserved. Okay, because it is lost due to heat because of friction. The other easy way to solve around this problem is work done equals to change in E mech plus change in E thermal equals to 0. So initial K2 plus U2 plus change in E thermal, right, equals to K1 plus U1. All right. So what we are trying to do here is, okay, at the bottom of the slide, right? So this is the where when you land at the from the slide, water slide, okay, you come to this point. Look at that is point 1. This is point 2 where you stop. You completely stop here, so kinetic energy is 0, potential energy is 0. So at this point, everything is in the form of kinetic, so potential energy is 0. So here, energy is so now whatever the energy you have is lost, but is in the form of heat. Okay, that whatever the heat energy was generated due to friction is work done by friction. That is friction kd, 1/2 mv final, mv squared. Sorry. So now, so friction kinetic is mu k mg d, 1/2 mv squared. So mass cancels out. So d equals to 1/2 v squared mu kg. Okay, that's another way to calculate that, and you should get the same answer, that d should come out to be 50 meters. I would prefer this method. Okay, whenever I say energy method, I don't want to see all your work. I would just like to see this. Okay, if there's a free body diagram involved, make sure you draw that free body diagram. Okay, this has been done. Okay. The figure shows a water slide, right, in which a glider is shot by a spring, okay, along water-drenched frictionless track that takes the glider from a horizontal section down the ground level. As the glider then moves around along the ground level track, it is gradually brought to rest by friction. So it is brought to rest by friction. So here you have potential energy due to spring and gravity here, okay, because spring is doing work as well. So everything is kinetic at this point, and then it stops at this point. Okay, stops here. Okay, so here you have energy due to spring, potential energy due to gravity. Here you have K, everything stops here. Okay, so we want to find this length L. Okay, simply you can start with work done equals to change in E mechanical plus change in E thermal. So you can write K at 2 plus U at 2 plus change in E thermal equals to K at 1 plus U at 1. Or you could have done K2 plus U2 equals to K1 plus U1 minus change in E thermal. Same thing, okay, because we are just playing with the equation. You could have done this as well. So I'm gonna make this point to be 1, this point here to be 2. I'm gonna skip whatever happens in between, okay? So at point 2, kinetic energy is 0, potential 0, right? At point 1, kinetic energy is 0. Change in E thermal equals to U1. Change in E thermal is mu times force normal, okay, mu K, force normal times length L. At there's two energy due to spring, 1/2 K x1 squared plus mg height 1. Okay, so now you can find length L, that is 1/2 K x1 squared plus force normal. Okay, so force normal is mg. Okay, so plug in those numbers. X1 is given to you. Is it given to us? Yes. Yes, spring compression at 5 meters. X1 equals to 5 meters. Okay, height 1 equals to 35 meters. Mass of a person is 200 kilograms, right? Mu K is 0.8. That's a lot of friction. Okay, K value is 3.2 times 10 to the power 8. So plugging in all those values, you should get L to be 69.26 meters. All right. So in this slide, okay, this is the summary of this chapter. Quick review of chapter 8. Okay, there are many more problems that you can practice. Okay, and it has solutions as well. Make sure you go through all of these. Okay. Okay, I'll be posting this slide. Okay, next time we'll be talking about simple harmonic motion. Okay. All right. That's all. Thank you.